And what it brings in from algebra is this method of solving linear or just graphing linear inequalities in two variables. All right, let's take a look at what you're bringing to this class, your knowledge of algebra at this point. All right, so we're mostly going to be interested in inequalities in 2 dimensions, but let me just refresh your memory about graphing in 1 dimension. I guess we did this back in chapter 1 maybe, but if you had like x is less than 5, something like this, on a 1-dimensional number line, we would put the boundary value, just make sure among other values we might have is to identify this boundary value and then put some kind of marking on it, you know, maybe a couple of numbers to the right and a couple of numbers to the left to establish a scale. And then what we would do is put some kind of marking on 5, and we would always graph the solutions. So this says x is a set of all numbers that are less than 5. So we're talking about all these numbers over here. These are the solutions. And we always shade the solutions. And we'd put some kind of mark here for less, strictly less than. A lot of times we'd put the open circle, but I think our author also uses the open parenthesis. So one of those two. We've done problems like this early on. If you had a greater than problem, like 7x greater than or equal to, 3x minus 16, something like that. Well, it's not as easy to just look at the inequality and graph it when you have something like this. So what you have to do instead is, get the 3x over, subtract 3x from both sides, and then finally divide by 4. And then that would give you x is greater than or equal to -4. So now the boundary value that I'll throw right in the middle is -4. And notice we have the greater than sign, greater than or equal to this time. And so we're always going to shade the solutions. So we're looking for numbers that are larger than -4. All those numbers appear to the right of -4. And then to indicate that we're going to include -4, maybe we would shade the -4. Have a solid dot instead of an open dot. The other version would be to have a square bracket. And that means we include the -4. Usually we put a couple of additional numbers along the scale. Looks like that. Okay, so what we can take from this is a couple of things. We need some kind of marker to identify the boundary. It's either a dot, square bracket, we include the -4, or an open circle or open parenthesis if we exclude the 5. The other thing is that we're always going to shade the solutions. So this is 1-dimensional graphic when we have just a single variable. What we do today, we will look at inequalities and graph them in 2 dimensions. So you're going to have an x and a y. Most of the time. And your inequalities are going to look like this. And you're going to be asked to graph them. Sometimes the y will be missing, but you need to know that you're in the 2-dimensional context. So you're going to be graphing, the left half of the Cartesian plane or the right half. And then here's the process. We're going to first, if you have an inequality that looks like this, the first thing we're going to do is replace the inequality symbol with an equal sign and graph the corresponding line. So if it was ax plus b is greater than c, or ax plus b is less than or equal to c, we're going to change the inequality to an equal and then graph the line as we normally would graph a line. Now the line becomes the boundary value. Instead of just a single number, it's an entire line becomes the boundary. And then we're going to shade one side of the line or the other. we're going to shade the solutions. And the way they do it here is they choose a test point. A lot of times they choose the origin, and then they're either going to shade, if the origin works, the 0.00 works in the inequality, then it's a solution. If it doesn't work, then it's not a solution. So if you test one point on one side of the boundary line and it works, that means all the points on that side of the boundary line work, and they're all solutions, and you'd shade it. You would shade those solutions. If the boundary, if the test point, the origin or some other point, does not satisfy the inequality, then it's not a solution. And if it's not a solution, you're not going to shade it. Rather, you're going to shade everything on the other side. Now, let's see how that works. So the first thing that you're going to have to be able to do is to determine if a point is a solution of a line. Well, maybe more down here than not. So if you want to know if this point, 3, 5, is a solution of this line, you have to plug in the x coordinate of 3 and the y coordinate of 5 into this line. If you end up with a true statement, then we say that the point 3, 5 is a solution to the line. So we're going to start with the equation of the line, and we're going to plug in 3 for x. At the same time, we plug in 5 for y, and we're going to write the equation with numbers only. And we'll put a question mark next to the equal sign, because when we're checking, we don't know if it's going to equal or not. And you can see this one does not equal. That's probably does not equal. So since the point does not work in the line, you're going to have a line that looks like this, and then you're going to have a point that's somewhere off the line. It's not on the line. So it's not a solution. So the answer to this one is no. We do something similar for inequalities. So let's take a look at, let me do number 3, and then I'll ask you to do number 4. So for number 3, it says, is the point 3, 5? And we're going to break that point apart into its two components, the x component and the y component. And we want to know, is this point in the solution set of, all right, now we're going to introduce an inequality. So the same idea, we're going to plug in 3 for x, we're going to plug in 5 for y, and we're going to see if now the inequality is true. If the inequality is true with those two x and y values inserted in, then we're going to say that the point 3, 5 is a solution to the inequality. Let's check it out. When we put 5 in for y, and 2 times 2x means 2 times x, and if x is 3, we got to multiply 2 times 3. Now we have an inequality, 6 plus 1, 5 less than or equal to 7. And so is this true? Is 5 less than or equal to 7? No, it's not true. And since it's not true, we say that 3, 5 is not a solution of y less than or equal to 2x plus 1. So the first problems are just, you're going to be testing a lot of points in these problems. And so they want you to get comfortable and know how to do that. So why don't you go ahead and try number 4. And a lot of times you can just plug the 9 in your head, plug the 7 in your head, and then work it out. But what we're after here, we know that the answer to number 3 was no. We just checked, it didn't work. What about number 4? Is the point 79 a solution of this inequality? And remember, the left and the right hand side does not have to match exactly, but the inequality has to be true. So yes or no? In the chat. Go ahead, write it in the chat. Okay. Yeah, since when we plug in our two coordinates into this new equation, we get a true statement, then that means that this point is one of many that are solutions to this. All right. The next thing that we're going to do, because when we solve these problems, these linear programming problems later on, we have to graph a bunch of inequalities. And so in this section, we just start off by graphing them. And then in the next section that we'll also look at today, we're going to graph several of these, and we're going to identify the solution set of a system of many inequalities. All right, let me take a look at one of these, maybe number 10, let's say. I'm going to get graph paper. Sometimes graph paper can be helpful, but y is greater than x plus 1. All right, the first thing that you have to do is to graph the boundary line. This is like graphing a line in algebra. So however you graph a line in algebra, you can use the slope intercept method. You can do a t-table and plug in a couple of points. But the boundary line is exactly as you see here, up here. But we're going to replace the inequality symbol with an equal sign. And then we're going to graph that line. So I'm going to do it here. Notice the inequality sign is strictly greater than. It's not greater than or equal to. I'll show you greater than or equal to or less than or equal to one next. So what we're going to do is graph this line however you want to do it. We need 2 points. You could choose, say, x to be 0. And if x is 0, y would be 1. You could choose if y is 0, then x would have to be -1. You could choose if x is 3, y would be 4. Y is always 1 more than x. All right, and then plot these points, 0, 1, -1, 0, 1, 2, 3, 1, 2, 3, 4. And you can see that we very quickly see a pattern, and here it is. Second, determine if boundary line should be solid or dotted. Dotted, I guess we could call it dotted. All right, first of all, this is directly linked to a solid line would be like this, or like this, something like that. And a dotted line would be something like this. The difference is that the line is not included, or I should say the points on the line are not solutions. And this is the one that you're going to select if you have a strictly less than or a strictly greater than sign. The solid lines would mean that the points on the line are solutions. And you will have a dotted line when you have a less than or equal to sign or a greater than or equal to sign. You'll have a solid. Now, our original problem had the greater than to it. So you can see of all these points on the line, if you take 3 and 4, where x is 3 and y is 4, and you put the 3 in there for x and the 4 in there for y, you're going to end up with 4 is greater than 3 plus 1. 4 is greater than 4. Now that's a false statement. So this point, while it's a solution to the line, the boundary line, it's not a solution to the inequality. And so in this case, whenever you have less than or greater than, in this case we have greater than, this line is going to be dotted and not solid. So that's one of the things you're always going to have to decide is the boundary line dotted or solid? If dotted, points on the line are not solutions. If solid, points on the line are solutions. Okay, so the final step is to determine which side of this inequality, you've got two sides separated by this boundary line. The solutions will be, in an inequality like this, either everything below the line or everything above the line. And so what we're going to do is to choose a test point to determine which side of the line to shade. And that's step 2. Choose a test point anywhere in the plane, not on the line. Can't be on the line. The origin is a good point to choose because it's very easy to evaluate algebraic expressions when we let all the variables be equal to 0. But you really can choose any point on the line. So let's test the point 0, 0. Let's write down our original inequality and see if 0, 0 works. 0, 0 on my graph is right here. And here's how we're going to reason. If 0, 0 is a solution to our inequality, then not only is this point a solution, then everything on this same side is a solution, and we would shade down underneath the line. If 0, 0 turns out not to be a solution, then none of the other points on the same side of the line are solutions as well. So we wouldn't shade this one, and hence we would shade everything on the other side. So we're either going to shade everything above the line or everything below. It depends on how our test point comes out. So let's check it. So we're going to put 0 in for y and 0 in for x. And we have 0 is greater than 0 plus 1. So is this true? Is 0 greater than 1? No, it's not true. So therefore, 0, 0 is not a solution. Okay, I'm going back up now. Since 0, 0 is not a solution, we don't want to shade it. We don't want to shade that point because it's not a solution. And since it's on the lower side of the line, we don't want to shade anything down here. None of them are solutions. You can check them all. Here's another one. This is the point 4, 1. You could see that 4, 1 doesn't work either. 1 greater than 4 plus 1? No, it doesn't work. None of the points down here will work. If you find one that doesn't work, then none of them work. Another way to say that is if you find one that a point that doesn't work, then none of the points on the same side are solutions, and everything on the other side of the line are solutions. So here's what we're going to do. We're going to shade everything above the line, and this would represent all the solutions. We can't possibly list them all, but all solutions come in the form of an ordered pair, an XY ordered pair. And if you check any ordered pair that falls in this shaded region, it'll work in our inequality. So let me just test one for you. 1, 2, 3, 4, this is -5. So this point right here is -5, 2. It's part of the shaded region, so therefore it's a solution. Let's check it. If we start with our original equation, y greater than x plus 1, and we replace the y with the y coordinate there, 2, and replace the x with the x coordinate, -5, we get this inequality that we can work out to be 2 is greater than -4. And yes, any positive number is greater than any negative number, so this confirms that -5, 2 is a solution. But those are pretty much the 3 steps. Graph the boundary line, decide if it's the easiest step is number 1, is it dotted or solid, the line, and then choose a test point to determine which side of the line you need to graph. Okay, now another one is that, can be tricky, but we're going to just apply the same steps. What you need to realize here is that, we're not talking about this problem that I did back here. X is greater than -4. We started off with one here that resulted in x greater than -4. But it's not this graph we want you to draw. we need to realize in the context that we're in, we're graphing Cartesian graphs in 2-dimensional. So x is greater than or equal to -4. We still do the same 3 steps. The first one is to graph the line, x equals -4. Now you might recognize that to be the equation that corresponds to a vertical line. There's no y. Y can be anything, but x has to be -4. So we go over to the x is -4, and we draw a line here, a vertical line. So here's your boundary line. Now it doesn't have a slant to it. It's not horizontal, so we really can't talk about above the line and below the line here. So what we'll do is we'll talk about to the left of the line or to the right of the line. All right, but the same idea applies. The question is, are we going to shade the right-hand side or the left-hand side over here? So if we choose a test point like 0, 0, well, there is no y coordinate up here. But if we test 0, 0, we do know that the x coordinate is 0, and that's the only thing really we can plug into that equation. If we plug in 0, 0, we get 0 is greater than or equal to -4. Well, that's true. So therefore, 0, 0 is a solution. So therefore, we want to shade 0, 0. And if we shade 0, 0, we're going to shade everything else on the same side of the line as 0, 0. So that we know 0, 0 is a solution, so everything on the same side of the line is also a solution. I drew this line in here. Is it supposed to be dotted like I have it drawn there? Or is it supposed to be solid?
It's solid.
Okay, thank you. Solid line because of the greater than or equal to. If it's equal to, we're going to include the points on the line. So even, you know, every point on this line, if you think about it, it begins -4 something. And there's not a y coordinate up here. So if we put -4 in for x, -4 greater than or equal to -4 is a true statement. That's greater than or equal to, and because it's equal to, we include it. So these vertical lines, you can do horizontal lines as well, where they're shading above or below the line. But you're going to have a lot of these half plane graphs here using vertical lines, particularly when we get to word problems. All right, we're also going to get into word problems immediately here. So you're going to get a lot of practice with doing those same problems that you've done back in your Algebra 1 class or Algebra 2. So there's a section in here where they just ask you to write down an equation, define the variable, one variable, I guess, and translate the sentence into an inequality. So it's, in our word problems, you're going to see things like at most, at least, greater than, less than, that kind of thing. There are fewer than 10 applicants. Define the variable. X equals the number of applicants. So define the variable and then write an equation. There are fewer than 10 applicants. X is less than 10. So X could be 9 or 8 or 7 or 6, and that would be true. So we're writing one-dimensional inequalities here. She consumes no more than 900 calories. X equals number of calories consumed. We'll always start the word problems and with defining the variables. If you don't define the variables, then we won't know what we're talking about. Or you might know, but I might not know what you're talking about. Okay, no more than. No more than. Could be 900, but can't be more than. No more than. Can't be 901, because that would be more than. No more than 900. Less than or equal to. 28. Y equals the discount. The discount is at least 5%. 5% or more. Could be 6%, 30%, 100%. Oh, that'd be nice. the discount y is at least 5%, greater than or equal to 0.05. Okay, go ahead and write number 27 in the chat box. Let's see, we have greater than or less than, yeah. So you can use the inequality symbols right on your keyboard, your computer keyboard. 27. Define the variable and then use it in an inequality. I guess if we're going to go less than or equal to, I guess we'll hit the less than or equal to and the greater than or equal to sign like that. Okay, yep. Okay, so it says it is over. So if you define, you know, x to be, it's like you guys have a good handle on this. X is over. So x is more than 3,000. Yep. So a lot of times what we do is we try to be brief, and we don't put in as many words as we really should to define a variable. So we're always going to define our variables in this class as quantities. So it's very important that when they say the monthly take-home pay is over $3,000, you use something more than just take-home or pay, because it has to be very descriptive. So monthly take-home pay would be this. Notice how I define my variables up here. Number of calories, not just calories, right? Number of applicants, not just applicants, but be sure that you define your variables as quantities. Quantities are things that are answers to the question how much or how many. All right, we'll get to more word problems, maybe even at this section. Yeah, end of this section, some more. All right, let's take a look at a problem that's already shaded for us, and we're going to do the reverse. So we're going to look at an equation, a solution set here. A couple of things you notice about number 34 is that there's a dotted line, and we'll also notice that we're shading underneath the line. So they want you to come up with the equation. It's not really an equation, it's an inequality, because your inequality is going to have a less than or equal to, greater than or equal to sign. And they want you to put it in ax plus by equals c form. So many times it's okay to just write it in y equals mx plus b form. That's what we're used to working with. But here they want it in a specific form. All right, so let's do number 34. We need the boundary line, and then we need to insert the appropriate symbol. All right, a couple of things I notice here is that we've got a couple of points. And if we have a couple of points and we write down the x and the y coordinates, particularly much easier to do this if your x and the y intercept are clear. You see what it is? The scale is marked from -5 to 5. So each one of these markings is a 1. And this point right here is on the y-axis. So this is actually the y-intercept. And then the slope, as we go from one point to the next, let's say if I start here and I want to go over to this point here, and I can only go vertically or horizontally, I want to go up 1, the rise is 1, and the run is 2. So rise equals 1 and run equals 2. So the slope is equal to rise over run, which is 1 over 2. So that's the slope. That's the value of m. And so we have y equals mx plus b. Even though I know we have to write it in that standard form, I'm going to start writing it in slope-intercept form, and then we'll get it into the ax plus by equals c form. All right. We know that the slope is 1/2, and we know that the y-intercept is the y-coordinate when x is equal to 0, so -1 in this case. All right, so this is what the boundary line looks like. But now let's convert it to ax plus by equals c format. So we're going to multiply by 2, get rid of the fractions. 2 times y, 2y. 2 and the 1/2 cancel out. So we just end up with x. And then 2 times the -1 is -2. Let's multiply everything by 2, gets rid of the fractions. We don't want fractions in ax plus by equals c form. A, b, and c are integers. All right, and then what we're going to do is to bring the x over to the left-hand side. And that gives us -x plus 2y equals -2. Now, sometimes there are advantages to writing this first term as a positive number. I think, in fact, some books want this first coefficient to be positive. So we can multiply everything by -1. And that'll change the sign of everything. X minus 2y equals 2. All right, we're almost there. Now what we have to do, this is the boundary line. Now we have to consider the shading. And so what we'll notice is that 0, 0 is not a solution. Well, maybe I should, instead of thinking about not a solution, maybe I should think of a point that is a solution. So I'm going to come down here into the shaded region, and I'm going to pick out this point right here. Since 5, 0 is in the shaded region, 5, 0 is a solution. So when I put 5, 0 into my inequality, it has to be true. Now, the other thing is that because the line is dotted, or dashed, or however you want to say it, then that means that the inequality symbols that we're going to use will either be the less than or greater than. We don't want the equal to sign in there, because as soon as we throw the equal sign under the inequality, then we've got a solid line. So we're down to the decision as to, do we want greater than or less than in place of that equal sign to complete the problem? And here's where the test point is going to come in. So we know 5, 0 is a solution because it's shaded. Therefore, it has to work in our inequality. So if I choose 5, 0, and I let x be 5, at the same time, I let y be 0, and I write everything else down. I'm just going to leave a blank here. What inequality sign has to go here to make this true? 5 is greater than 2. So if we want 5, 0 to be a solution, then the symbol we need to put in there is the greater than. So the final answer to our problem, we have the boundary line, but we're going to insert the greater than. So x minus 2y greater than 2. And there's the inequality that matches that solution set. Go ahead, write number 36 in the chat. Kind of looks a lot like this one we did earlier. Vertical line shaded on one side or the other. Okay, vertical line, x is equal to -2. But if we want an inequality, we're either going to have x is less than or greater than -2. And the reason it's greater than or less than is because, again, we have a dotted line, so we don't want the equal sign there. And all these numbers over here are less than 2. So x is less than or negative 2. There's the inequality. Some more word problems. They're actually word phrases. But in this case, we have to define 2 variables as quantities. So x equals something and then y equals something. Define them as quantities and then use those quantities in an inequality. So here's one that number 40. Let's let x equal, all right, new car sales, used car sales combined are at most 500,000. Okay, so I guess we could just call it new car sales, although that might mean the number of cars sold. So I'm going to say revenue from new car sales. And then Y would be something similar, but revenue from used car sales.
Yeah, let's talk later.
Other. Okay, so so we have new car sales and used car sales, and they say that that amount together, when you combine them, is at most 500,000. At most. Could be 500,000, but it can't go over 500,000. It can be at most 500,000. So X, the revenue from the new car sales, plus Y, the revenue from the used car sales, together can be at most less than or equal to 500,000. You're going to be writing lots and lots and lots of inequalities like this in these linear programming problems. This is just one phrase or one sentence that you'll see in a word problem that might involve 3 or 4 of these. And you have to write 3 or 4 of these. All right. 42. Isn't this an interesting question this time of year? Yeah, it might even be true, right? The Democratic candidate beat the Republican candidate by at least 7 percentage points. So define X and Y as quantities. In this case, it's percentages, percentage points. So percent of vote for Democratic candidate, and Y would be percentage of the vote for the Republican candidate. Be sure you get out and vote if you haven't already, either the day of, or if you've got that mail-in ballot kind of sitting around the house, fill it out and send it in by at least 7 percentage points. All right. Now, if one beat the other one and the Democratic candidate beat the Republican, then the Democratic candidate's percentage is higher than the Republican candidate's percentage. And so to get a positive number, we would subtract in this way. It's the difference between those 2 percentages. The difference would be how much one candidate beat the other one by. Is at least greater than or equal to 7 percentage points. I think we can say 7 here because we defined X and Y as percentages. So at least and at most, when you see those two, they are going to include the equal sign with the inequality symbol, at least, at most. Okay, we'll get to one of those word problems. Why don't we just go ahead and do one right now? 56. Labor costs for a farmer are $120 per acre for corn and $100 per acre for soybeans. Could be farmers around here. They plant a lot of corn and soybeans around this area. Sugar beets is another big one. How many acres of each crop should the farmer plant if he wants to spend no more than $15,000 on labor? All right. I'm going to recommend that you go through this process, because if you do it, a lot of times you can just see the inequalities just revealed and right on your paper from just your what you define. So we're always going to define our variables as the things we're looking to find. And in these problems, we're looking to find two things. How many acres of each crop? All right. So X equals the number of acres of the first crop. We'll call it corn. And Y equals the number of acres of soybeans. Now, right next to those, just write total over here. And we're going to create this little grid. And inside the grid, you're going to see your two equations up here. And we'll even give them a theme. Might be one equation, might be two equations, might be 3 or 4. Could be as many as we want. All right, labor costs. Someone's got to plant the corn, got to fertilize corn, water the corn, and in the fall, harvest the corn. So all this is labor stuff. And it costs for all of those different instances. And so labor costs for a farmer are 120 per acre, and we have X acres. So it's $120 per acre. How many acres do we have? X of them. We've just defined it up here as to be X is the number of acres. So if it's just 1 acre, then it would cost $120. If it was 2 acres, $240. Just whatever the number of acres that are planted, just multiply it by 120. And labor costs still, labor costs, soybeans, labor costs, soybeans, $100 per acre. But we've defined the number of acres of soybeans to be Y. So if we add those two together, we get the total labor costs. All right, how many acres of each crop should the farmer plant if he wants to spend no more than $15,000 on labor? All right, so here's the labor costs. And we don't want to spend more than $15,000 on all of these costs. There's costs associated with planting and harvesting corn, costs associated with planting and harvesting soybeans. So we want this amount no more than, cannot exceed, at most. So no more than is the same thing as at most. So the labor cost has to be less than or equal to the 15,000. So this is a dollar amount, and this is a dollar amount, and this is a dollar amount. You want to make sure that when you write these equations that all your units are the same in any one equation or inequality. Okay, now there's two other inequalities that are in this problem. Did you see them? I think we've handled all the information from this problem, but there are two inequalities that are implied that you don't actually see them because it doesn't silly to actually state them in a word problem. And they are this. The number of acres that you plant cannot be negative. You can't plant a negative number of acres of corn. You can't plant a net negative number of acres of soybeans. So X, which is the number of acres of corn, has to be positive. It just doesn't make sense to have a negative number of acres of corn. So here's an inequality that doesn't appear in the problem, but it must be one of the inequalities that we include. For this context of this problem, same for Y. So we actually have 3 inequalities. And there's really only one that we can pick out of the problem. We just need to know that in this context, these variables that we define cannot be negative. Suppose we can plant 0, but we can't plant a negative. All right, so the reason we did this, I wanted to do this one first because you might wonder why we have these problems here. And notice there's one inequality plus x greater than or equal to 0, y greater than or equal to 0. These two constraints are some that we almost add to all of our word problems because almost always we're dealing with positive quantities. Okay, moving on. Now we're going to solve systems. Now, systems of linear equations, the problem was, okay, you have this line here, and you have this line here, and the goal was to find the common point. That common point was the solution. Graph one line, graph the other line, see where they intersect. We did it, in fact, even earlier in this semester. This is going to be part of what you do for these linear programming problems, but we're not there yet. We'll get there next time. What we're going to do, and what you're going to see here, is you're going to see several different inequalities. Now, when you see these two here, that means that we're just talking about the first quadrant. Usually we're going to see these two in application problems where we don't want negative x to be negative and we don't want y to be negative. It just doesn't make any sense for the problem. So it's going to help you out a little bit when you automatically know if x is greater than 0 and y is greater than or equal to 0, then you're talking about only the solutions the only solutions would be in the first quadrant. All right, so the solution set when we have a system will be all of the points that satisfy both or 3 or all the inequalities in the problem. So what we're looking for here is if you have this system where you have 1, 2, 3, 4 inequalities, you're looking for solutions, or the definition of a solution would be a point that works in all 4. So you don't check a point in just one of the inequalities, you have to check the point in all 4. And in order to be a solution, the point that you're checking has to work in all 4 inequalities. So let's take a look at number 6. We have the point 5, 3. And the question is this a solution? Not to a single inequality, but of the whole system of linear inequalities. We know in that point, the x coordinate is 5 and the y coordinate is 3. So we're going to take those two values out and plug them in. 5 times x is 5, plus 3 is less than or equal to 32. All right, we got to check that one, make sure it works out. 7 times x plus 4 times y, okay, x is 5, y is 3, is greater than or equal to 45. All right, now this next one, x is greater than or equal to 0, there's no y in there, so we only use the x coordinate, 5, greater than or equal to 0. And in the last inequality, there's no x, but there is a y. And the test value we're checking, the y coordinate is 3, greater than or equal to 0. So you have to check all 4 of these. And if all 4 are true, we're going to say that the point 5, 3 is a solution. All it takes for 5, 3 to not be a solution is that it fails to be a solution in any one of those 4 inequalities. So we'll check them out. This is 25 plus 3, that's 28. 28 is less than 32, that one checks out. 35 plus 12, that's 47, greater than or equal to 45. Yes, that's true. 5 is greater than 0, that's true. 3 is greater than 0, that's true. All 4 are true, so the answer is yes. 5, 3 is a solution. Okay, let's take a look at these. And I'll do, maybe I'll do number 14. And we're going to have multiple inequalities. We have to graph each one, shade each one, and then we're going to say the solution set would be all of these, since we have two inequalities here, would be the doubly shaded region. So we're going to graph and shade one, graph and shade the other, and then look for the doubly shaded region. So what will be helpful to you right now would be to use multiple colors. And I'm going to use graph paper just so I can be a little bit more accurate. I'm going to write down the two inequalities, and then we're going to solve each system. So when it says solve each system, we can't possibly write down all of the points in a shaded region. There's just an infinite number. So what we do to write the solution is actually just draw the graph. The graph is the solution. All right, so let's start off. And we really have two problems like we did in the first section. 3x plus 4y. To get the boundary line, we're going to insert an equal sign instead of the less than or equal to. And then we'll find a couple of points that work on that line. And then we'll graph it. Intercepts are nice for this one. If x is equal to 0, and I put 0 in there for x, 3 times 0 is 0, so I just have 4y equals 12. If 4y is equal to 12, then y is equal to 3. So 0, 3 is a point on our first line. Another point that would work, I've got the y-intercept, why not try the x-intercept? Let y be 0. If y is 0, then that term goes away, and you get 3x equals 12. Well, x must be 4 in that case. 1, 2, 3, 4. I see I have a strictly less than or less than or equal to sign, so my line is going to be solid. Just line up those points and draw the line. All right, which side of this line is shaded, above or below? Above or below? Which one? Write it in the chat. Where do I shade? Tell me where to shade, above or below? Okay, good. So remember, you can't go back to the equation because if you choose a test point, or a test point is not on the equation, it's not going to make sense. You got to go back to the inequality, plug in a point like 0, 0. 3 times 0 plus 4 times 0 is 0. 0 less than 12 is true. So 0, 0 works. 0, 0 is a solution. And since it falls underneath the line, not only will 0, 0 be a solution, but everything underneath the line will be solutions. It looks like that. The next inequality is y greater than or equal to -3. Now this is, we're going to start off with y equals -3, replace the inequality sign with an equal sign. And that's the equation of a horizontal line. There's no x in it. So I'm going to draw that line at -3. It's greater than or equal to. So we're going to draw a solid line, -1, -2, -3. There it is. This is y equals -3. And this is 3x plus 4y equals 12. So when I label the lines, I'm going to label the actual equations. All right, here's y equals -3, and our inequality is y is greater than or equal to -3. So do I shade this one above or below? Above y equals -3 or below? Here's the inequality. So any point up here would have a y coordinate that is larger than -3. So you're correct. You're going to shade everything above the line. Okay. Now the solution set is the doubly shaded region. And so when I actually write the solution down, this is all shaded here. So here is shaded both red and purple. And so the shaded the solution set would be this blue shaded region here. There. Any point in the blue shaded region here, if you use it as a test point, it'll work in both of these inequalities up at the top, this one and this one. Any point out here will work in one, but not the other. Any point over in this little region will not work in either of the two inequalities. And this purple region down here that's not blue, this will work in the one line, but not the other. One inequality, but not the other. It's only these blue shaded regions that'll work in both. Now, one other definition here, couple more, in fact. This region is not enclosed on all the sides. It's not like a rectangular shape or a polygon of anything that has certain sides to it. It goes on forever in here. And if that's the case, we call this an unbounded region. And some of your problems today will just ask you that. Is this region bounded or unbounded? Here would be an example of a bounded region, something like this. If you had a region that looked like this, and this was the solution set, and it didn't go off in any direction infinitely, this here would be a bounded region, completely enclosed. Bounded, unbounded. The other thing that you're going to be asked to identify is this point here where two of the lines intersect. It's on both boundary lines, and it forms a corner, and we call this a corner point. And you're going to be asked to find these corner points in these problems for today. And it turns out that in the linear programming problem that we do later on, that corner point is one of the prime candidates for the solution to the linear programming problem. So what your job is to do today is just to identify the coordinates of that point. Right there. Now we know that it's on the line y equals -3. So we do know that the y coordinate is -3, but we still have to find the x coordinate. So if you take the 3x plus 4y equals 12, just work with the boundary line as opposed to the inequality. And if you know that the point you're looking for has a y coordinate of -3, you could just plug in -3 in for y and solve for x. And this just involves a little algebra. And what you get should make sense. So that point right there, 1, 2, 3, 4, 5, 6, 7, 8. So the corner point is the point 8, -3. And you can confirm it on the graph. You can confirm it using algebra. So find the corner point.